Before we get started, I want to just say a very special thanks to Megan Gill, who's sitting in the back from 10Gen. 10Gen's been hosting, obviously. She was good enough to scramble for pizza this afternoon, and she also helped with getting Elliot speaking last time. So she's been actually almost feels like part of the team right now. So thank you very much, Megan. Tonight, we have Gregg Donovan from the search infrastructure team at Etsy. Gregg and I actually started at Etsy 3.5 years ago, right around the same time, almost like the same week, if I recall correctly. Our paths crossed mostly because I worked on starting the site performance team at Etsy, and I was constantly looking at how quickly or slowly our pages were loading, and as we look at these little charts of across the day, we'd see these spikes in how long pages would render, especially around search, and kept going to the search team and trying to figure out what's going on. And Gregg would say, well, that's kind of garbage collection. And so tonight, this is one of the things that I think Etsy excels at is dealing with these sort of anomalies in our infrastructure and really tightening things up, providing something that's very fast and resilient. Tonight, I believe that Gregg is going to be talking a lot about how we deal with garbage collection as an anomaly within the JVM and how we deal with that in the search stack. So please welcome Gregg Donovan.
Hello. So I'm going to be talking about designing applications. Let's see, where should I stand? This is good. Designing applications for garbage collection. So when you have a system with a garbage collected runtime, how do you design your systems? So this could be the JVM. It could be Ruby. It could be any garbage collected runtime. The basic concepts should apply. But our experience is coming from a web stack that's built on PHP and Apache, speaking to Java-based search processes, the foundation of which is Solr and Lucene. So that's sort of how the Etsy search infrastructure works. So let's see. A little bit about myself. Get myself set up. Been working on search engineering, as Mike said, for 3.5 years at Etsy. Before that, I was at a company called The Ladders, another New York City tech startup, working on search recommendations and web infrastructure. So this talk is about designing systems. So this is not we're not going to go into incredibly low-level detail about the JVM garbage collectors and every flag you might be able to tune. This is more of a general application design talk, but I will point you to some resources for further information. But the big starting point is to get a good mental model of garbage collection and how it works, and not think of it as quite so much of a black box. Be able to understand what's happening inside the application. And so as we go, if you have questions, please let me know, raise your hand, and we can do questions as we go. So about Etsy. Etsy is an online marketplace for handmade goods, vintage items, and craft supplies. We have millions of unique items from sellers in more than 150 countries. We connect shoppers with independent creators from around the world, and providing artists a platform to create their own businesses. So there's a lot of very unique items. There's more than 25 million members now. More than 20 million items, 20 million active items. So that's searchable items. So as search infrastructure, that's the number for us. How many are searchable? Over 900,000 active sellers from around the world. And the number that keeps going up and up every time I give a talk, I have to increase that number. More than 60 million unique monthly visitors. And so some very, very unique items on the site. A lot of very creative sellers. These are one of my favorites. Actually, something I have by my desk. These are Syscall distribution pillows. So there's 6 of them here. If you can name 3 or more, please come talk to me about jobs in data science. If you can name all 6. So lots of great stuff. It's a really, really fun site to work on. It's got a lot of very unique search problems, a lot of very unique search and data and recommendations problems because most items are unique and handmade. So let's keep those guys up. Because most items are unique and handmade, it makes for very interesting search problems and very interesting recommendations and discovery problems, because as soon as we sort of get enough data to be able to tell you about an item and recommend it well and use it in search and discovery, somebody buys it and it's gone, because then there's only one of it. So how do you deal with that sort of thing? So it's a very different search and discovery problem, recommendation problem than something like Amazon, where you have mass-produced items where they'll live in the marketplace for 15 years, and you can get reams and reams of data on them. So it's more challenging in certain ways. So Etsy has, we're right here in Brooklyn. We've got, I guess, about 145 engineers. I can no longer fit them all in one slide. This is about half of them. It's a great organization. A lot of folks from Google, Flickr, Yahoo, Microsoft. Very pragmatic engineering culture. These are screen printed by our CTO. We've got an engineering blog we invite you to check out, Code is Craft, where we publish everything from site performance reports to MySQL to PHP to stuff about our deployment. We're a continuous deployment shop, so we deploy the site something like 50 times a day now, and we also continuously deploy our search infrastructure, which will come up later in this talk. So you never know, as you're designing how your search infrastructure is going to work, when those things are going to go away because they're being deployed to. So that creates, our velocity itself creates some interesting challenges. And actually, if you're interested in search-related topics on our blog, we talk about our BitTorrent-based index distribution, which is pretty interesting. So we currently use BitTorrent to ship large indices around the data center, and we also talk about relevance tuning and things like that. So those are some of the search-specific slides. So we're talking about understanding garbage collection, building up sort of a basic mental model of how it works, how to monitor it, how to know when it's happening, why it's happening, the details of what's happening. Some basics about debugging memory leaks. Just because you have a garbage collected language in runtime doesn't mean you can't have memory leaks. And they can be particularly insidious, but there's a couple of good techniques I've found for finding them. And then finally, probably the most important part, which is designing for partial availability. When you have a system that might go away because of a garbage collection pause, you have to design for that. And so we're going to talk about that. I'd like to get a sense, though, of what sort of runtimes people are using. So just hands. Who's using the JVM? How about Ruby? How about Node.js? How about Go? About something I haven't mentioned? Okay. What's the something I haven't mentioned? Mathematica. Okay. Mathematica? Yeah. Interesting. We actually had Mathematica. Oh, no. We actually at one point had MATLAB running on EC2, but that's a story for another day. All right. So if you're like me starting out with garbage collection, you realize you have a problem with garbage collection, your application is pausing, it's garbage collecting, and it's a bit of a mystery as to why first. What is happening? It's a bit of a black box, and very quickly you can start to look into the various tuning parameters, and it's a little opaque. So to get into it a little bit, I want to start with a very basic example, and then we're going to pretend to be the JVM, and we're going to go through and do some garbage collecting, and we're going to just sort of work through what's happening. So this is a piece of production code I wrote today. No, this is a silly example. So this is this little buzzword detector. We're going to go through. We're going to send it some parameters, and then we're going to see which buzzwords match. But so let's walk through it. What do we have here? We have a static array of strings. The prefixes. We have another static array, and so let's walk through it. This one I got to walk. So we're going to assign args to my args. We're going to go through the loop once, and then we're going to assume that we've run out of memory. So we go through the loop the first time. We're going to lowercase a string. And inside of 2 lowercase, you can assume that there's some allocation that needs to happen. We need to allocate a new string on the heap for this new LC variable. And then, so where is this stuff getting allocated? So we've got allocation happening on the heap. And then the references that point to the memory on the heap is getting allocated on the stack frame of our thread. So main is just another thread that gets executed, and it's got its own stack. So we're going to go through here. Contains allocates to memory. And so we get to the end. Let's assume we get back to here. We need to allocate memory into lowercase. So what happens in the VM? So we've run out of memory. Let's assume we gave this thing very little memory, and now we need to garbage collect, and we need to free up some memory. So what happens there? How does it work? So the basics of garbage collection, the most basic algorithm is, so let's go through a basic allocation step. So we need to allocate memory. If you can't allocate memory, you do a garbage collection. And then you try again. And if you still can't allocate memory, you're out of heap. And you're out of memory, so you get an error. But when you can collect, so we're going to go through a basic mark and sweep algorithm. And so we're going to first start by finding the roots, the roots from which we're going to traverse our memory space, from which we're going to traverse the heap. And so what are the roots? So in our application, we're talking about things like threads, statics, registers. So the VM is going to start with those, and then it's going to walk their references, and then walk their references, and sort of traverse that entire tree of references, marking each one of them as live. And then everything else will be assumed to be garbage. And that's the basics of mark and sweep. So from each root, set it as marked, go through, and then when you're done, everything else is garbage. A basic tree traversal using the roots. And so if we go back, so what are the roots here? So the roots, we've got these statics, the 2 static arrays. We've got the stack frame of our thread. And so if we go through, we would start with prefixes, and we'd walk its references. We'd start with myargs, we'd walk its references. We'd look at the stack frame, look at variables that have been allocated, and go through and mark those. So we'd mark args as live. We'd mark, let's say we're right here. That would be about it for things that are live. And so the things we've allocated in the previous loop, they would not get marked. So the things that were local to the first loop of this, those would not get marked. And so if we're doing the mark and sweep, we could then, let's say, add those slots that those things occupied to a free list, and then we wanted to allocate, we could use those slots. And so let's say we go through the loop again, second time, and we wanted to do this process, right? So we go through, we allocate more memory here, we allocate more memory here, and then we run out of memory again, we need to do another garbage collection. So you'll see we have to go through the same process again, hitting prefixes, walking its references, hitting myargs, walking its references, and then doing the same thing for main. And that sort of leads us into, get back to that, sort of leads us into the weak generational hypothesis. Weak generational hypothesis, which is that in most applications, there are very short-lived objects that exist for a very small amount of time. Like in a web application, you'd have, say, request-scoped objects would be very short-lived objects. You'd have things like caches that live for a long amount of time. So if you can somehow segment your memory space into these short-lived and long-lived objects, every time you do a collection, you won't need to traverse every single object that's ever been allocated. And so we'll see how that works inside the JVM. So I had a trivia question here, though. Who invented garbage collection and the mark and sweep algorithm? Anyone know? Comes from Lisp. John McCarthy, the creator of Lisp, in 1960 invented garbage collection for Lisp, and with it the mark and sweep algorithm. So it's useful once you start to think about most modern runtimes having using the weak generational hypothesis. It's useful to think about in your application, where do your applications live? What sort of lifetimes do they have? Are they short-lived? Are they long-lived? And the longer lived they are, we'll see they become more expensive to collect. So a bit of terminology as you're going through things about garbage collection. Concurrent versus parallel can be a little bit confusing. Concurrent is basically work that the garbage collector is doing while your application is still live. So your application is still executing code, things are still happening. If something is happening concurrently, like there's a marking phase happening, that's happening concurrently. Whereas parallel would be you're doing a full collection, but it's happening in parallel, multiple cores are being used. So the different JVM collectors, we'll go through these very quickly. So the serial collector uses the weak generational hypothesis. It's a single-threaded stop-the-world copying collector, which means a copying collector basically means you go through that mark phase, and then you take the objects you've identified as live, and you move them to a new space. And then you know that everything in that old space can be wiped away. The entire thing can be used for allocation. So this is entirely stop the world. All phases of it are stop the world. The throughput collector is a multi-threaded stop the world copying collector. So it's got a new generation where short-lived objects live. It's got an older generation where once you've tried to collect an object a certain amount of times, it ages out and it gets pushed into the old generation. So going back to our example, those static strings would eventually move their way to the older generation. So once we try to collect them a certain amount of time, you see they're still there, between 1 and 15 times, depending on how your JVM is collected. They'd get moved to the older generation, and then new generation collections wouldn't need to look at them at all, wouldn't need to traverse them. So that's how you end up having very, very fast new generation collection times in the VM, is that these objects get moved out. So the CMS in the JVM is the concurrent mark and sweep collector, and this attempts to do a lot of work in parallel. So it tries to do a lot of the marking phase, traversing that graph of references, tries to do that in parallel to your application running. You can't do everything in parallel. Like, try to imagine doing that copying, the moving of references while you're still executing code. It doesn't do that. So once it has to actually move objects around and repair references and retarget where objects live in the heap, that it has to actually stop the application for. But it tries to do as much of the work as it can in parallel. And so that's why it attempts to have the pause times as low as possible. So this is used for a lot of apps that can't really tolerate any sort of pauses. And then the successor to the CMS collector is the G1 collector. So it attempts to work around some of the deficiencies in the CMS collector. So what this does is it divides the heap into lots of different spaces. And then in parallel, what it's basically doing is trying to find which of the different spaces of the heap has the most garbage, which one would be most beneficial to clean up. So thus the term garbage first collector, tries to find the garbage first. And then there's a commercial collector that is worth mentioning, which is the Azul C4 collector, which is by many benchmarks the best JVM garbage collection technology out there. It's just commercial, which is unfortunate. But it can run 100 gig heaps with 10 millisecond pause times. It's really quite nice. It'd be nice if that were part of the JVM, but it's not. But if you happen to work at a company that has copious amounts of free cash and you have garbage collection problems, please ring up the people at Azul and they will save you a lot of time. Then there's other JVMs. There's the IBM one, the Dalvik one. I don't know anything about those. There's a big amount of freedom you get to implement the JVM. So these could be very different. So at Etsy, we use the throughput collector. And so we're going to, especially as we talk about designing for partial availability, we're going to get into why we use this throughput collector and what the advantages are. So as we had, as Mike said, we had big problems in search with this spikiness, user-facing latency that we could attribute to garbage collection. And so the first thing we did is we went in using the CMS collector and tried to minimize the pause times. So we tried tuning the new generation size, tuning the amount of times objects had to be attempted to be collected before they got tenured out to the old space, trying to put off the expensive old generation collections as long as we possibly could. But we tried, and we just could not get it to stop pausing, which I think is an experience most people have. Garbage collection is going to happen. So that was sort of phase one. And then phase two, we were able to try the throughput collector. We will sometimes get very large pauses, sometimes multi-second pauses, but they were fairly predictable, and the JVM was resilient. We knew it would come back. It might pause for a few seconds, do a big old generation cleanup, but it would come back and it would run smoothly. And it got the overall pause time over the course of the day would be something between 1% and 3%. So we were very happy with the availability, but we had the pauses to deal with. And so in the part about designing for partial availability, we'll talk more about how we worked around that. But so let's see if there's any questions so far.
What's your heap size?
What is our heap size? In our main application right now, it's 31 gigs. But as I'll talk about also later, is for our main listing search, for the main user-facing search application. But that is actually something we're looking to change. And in the newest application we're working on, they're half a gig. So they're sort of micro-sharded, highly sharded, very small JVMs. And the idea being that to just basically give the garbage collector less work, make it, once the old generation gets to a certain size, you're gonna have a pause. It's gonna take a certain amount of time. So if you can give the JVM as little work as possible, the pauses will be smaller. Any other questions? Okay. This is the least exciting part, which is the monitoring. So how do you know GC is a problem? So your application is garbage collecting. The people in application performance are complaining. How do you know that it's actually garbage collection that's causing you pain? So the first thing we did, or one of the first things we did, is we tried to figure out how much time you're spending per user-facing request on garbage collection. And this was key for us because you can look at what's the percentage of time your application is spending in garbage collection, and it could be 1%, it could be 4%, it could be 10%. I mean, lower is better, but if it actually doesn't impact user-facing performance in a way that you care about, then it's not really a big deal. What you care about is if it actually is bumping up user-facing latency. So what we did is, in each request, we'll record the total amount of time the JVM has spent in garbage collection, put it in a thread local at the end of the request, do the same thing and take the diff, and then put that in every log line and record that. So let's just see, if you have, let's say, a 4-second query, was that the result of something actually expensive, or was your application paused in garbage collection? Before we did that, we would often spend time chasing down what we thought were slow queries that were actually just the application pausing for garbage collection. So it's very clarifying to have that in the logs. And it's pretty easy to get that.
Correct. This is happening on specific requests, not every request?
Happening every single request. Every single request. So we've got a threaded thread pool receiving requests, and each of those threads, as it reads a request, will go to the overall JMX bean, where the JVM will tell you total how many milliseconds it's spent in garbage collection in its life, and then at the end of your request, at the end of that thread's handling of the request, you can check it again, and then it'll tell you just for that particular request how much of the wall clock time was garbage collection. And you can get it to tell you the number of collections if you want, but really you just need to know was that GC time. Then you can look at, just graph your GC time over the day per request, and that's been really useful for us. And then you're also going to want, well, I would say actually, so when there are GC problems, the first thing I actually like to do is to look at the VM while it's going. Look at the different spaces in memory, watch the collections, watch the heap grow and shrink, watch the JVM, and you can kind of get a sense of if it's healthy and if it's functioning correctly just by watching it. And so here's an example of one of our servers and what visual GC will tell you. So you can see here's the old generation, here's the new generation, the Eden space, and these are the different survivor spaces where objects that have not been moved to the old generation but have survived a few garbage collections have been moved to. And so you can watch these graphs sort of go up and down. You can see the total time spent in collections, the number of collections, and if you depending on whether you've tuned these different spaces yourself or whether you've let the JVM kind of auto-tune it, you can look at how big is Eden, how big is old, how full are these things. One thing there's not any sort of good visualization I've found anywhere for is fragmentation. So it won't tell you if the old generation is totally fragmented. And that's something that might catch up with you at some point, but I haven't actually found any good visualizations for that built in. So this is really helpful just to look at it. So you're also going to want to get more detailed logging information out of the JVM or whatever runtime you have. This is what we use. These are our GC debugging options. Let's see. What's interesting about these? It'll tell you nice things like how long your application stopped, how long it ran for. If you're using adaptive tuning, the JVM can tell you all of the adaptive tuning changes that it made as it was running. And then it can also tell you interesting things like save point statistics. So GC is not the only thing that JVM will stop for. It will also, let's say it's going to de-optimize or optimize a stack frame. It has to stop the JVM from running. And most of the time when it's slow, it is GC, but sometimes you'll get save points that are, you have to, not every JVM instruction is a save point. Sometimes the VM will have to sort of wait till the application reaches a save point where it can actually pause it. So this is what we do, and then so you end up with a log file. So this is unfortunately the way the JVM works, or at least the Oracle JVM. This stuff you can't kind of format nicely with log4j and pick stuff out and format it. It just goes to a raw log. And it looks like this. It's pretty dense and kind of hard to look at. But this is actually a real capture of a very unhappy server we had at Etsy in our testing environment. And you can see some of this stuff. You can see it's printing the heap after a GC invocation, and you can see the Eden space, and then the object space is still 99% used even after a full collection that took 137 seconds of user CPU. So this thing is toast. So that's you can look at these things by hand and analyze them, and you get to know what's happening. But there's also some log analyzers that can take these things and make some sense of them. These are sort of the historical log analyzers that have been out there. Netflix sort of set the standard this year with something called GC Viz. It came out recently, which actually gives you really nice visualizations of these GC log files. So that's worth looking at. One thing we do is we use something that Mike actually helped us create, which is a logging framework called Logster, where you can write these little small Python utility class to go through a log file like that, pull stuff out, and then we spit the metrics to Ganglia. And so we end up with something like this, where we can see the ratio of stop time to application concurrent time. And then, if you have these in graphing, you can correlate them with other metrics. And then once you get enough metrics, you're going to want to have a dashboard. And so Actually, another thing I think Mike helped out with is, I wasn't even intending this, is our dashboarding framework, which is really, really nice to end up with these sweet dashboards where you can aggregate your metrics together. They could be from different graphing sources. So here's, you've got things like the new-gen heap, and you can slice them by hour. You can correlate deployments and other events, which are the vertical lines. So that's been incredibly helpful. Also been very helpful for us for analyzing the heap. So let's say you want to know, okay, it's garbage collecting, the old generation is full all the time, and what's all this memory, what is it? Your kit is sort of my tool of choice for analyzing the heap. So you can start it up, you can start memory profiling, you can get a dump, and it's got great tools for actually taking the heap itself and slicing and dicing, looking at actual objects, looking at paths from roots. It's terrific. It's commercial, but totally worth the money. And I'll show you some neat features of it a little bit later, looking at memory leaks. But so let's talk about designing for partial availability. So we're monitoring GC. We're doing our best to keep it under control, but things are going to pause. Servers are going to go away. So one of the first things we thought to ourselves is, all right, if a certain portion of our server pool at any given time is going to be garbage collecting, how do we work around this? How can we not send, if we could just know that, let's say we're going to spend 6% of our time in garbage collection, but if we happen to send a request to a server that's garbage collecting at that moment, we're not going to hear anything back. What if we could just know that it's garbage collecting and not send a request to it? Then we could avoid these problems. So the first thing we tried is a clever little hook inside the C interface in the JVM called the JVM TI, the Java Virtual Machine Tooling Interface. And so we wrote a little C program that got a notification when the JVM was about to garbage collect and when it was done. And what we did is we used that to set an IP tables rule to block all traffic coming to that node. So it was very blunt. And this worked really nicely. Requests did not come in when it was garbage collecting. But as you'll see, if you look at your logs, most garbage collections are very, very fast. They're like less than a millisecond. And it actually takes something like 50 milliseconds to shut that network interface down and then bring it back up. So it was a win for not sending a request during like a 5-second garbage collection, but every other time it was a complete disaster. But I still feel like there's something there. Like if the JVM had a hook like, I'm going to do an old generation collection, then this might be worth it. So that didn't work. So how can we ignore or at least quickly move through a host that's busy garbage collecting? Your first thing is, well, won't it just not accept a socket connection? Like if you're just trying to connect to it, won't it just deny it if it's in the middle of if it's in the middle of a stop the world collection, won't it just stop talking to you? And it won't. Unfortunately, the operating system will lie to you. The machine you connect to is going to accept that socket. And then you could write bytes to it. You could send your request to it, and it'll receive those bytes. And then you'll sit back and you'll listen for a response. And you'll get nothing because the JVM is not running. The JVM is busy garbage collecting. It'll get back to you in 10 seconds. So how do we deal with this? So we thought about, well, we just need to verify that the JVM can do anything. Like it just needs to be able to run some Java code. Some JVM instructions have to run, has to do something. And if we can verify that, then we've got a much better chance of actually getting it to answer our query. So the thing we came up with is called a banner protocol. So we make a TCP connection, and then we don't do anything. We don't send a query. We just wait somewhere between 1 and 10 milliseconds. And either we don't just wait. We read. We read from the socket for 1 to 10 milliseconds. And either we receive a magic 4-byte header. Here's our magic 4-byte header. I have stickers of them, and I have a slide. Either we receive our magic 4-byte header, or we just move on to another host. And so what this does is on the server end, on the JVM end, you have a little bit of code that just has to accept the socket, When the socket is accepted, it just writes the 4 bytes out, and then it goes back to processing request as it normally would, waiting to read the request and then processing it. But it ensures that it's not doing a full stop the world garbage collection because it had to do something. The JVM actually had to execute instructions to get us those 4 bytes. So this was great for us, and I can actually show you some of the code for doing this. This is the PHP side of it with some bits of error handling and logging and stuff elided just so it fits on a slide. But basically, open a socket with whatever your socket connect timeout is, and read 4 bytes, unpack the bytes, and if it doesn't match the closest hex bytes I can come up with that matched code as craft, if it doesn't match those, or it just times out, if it hits that 1 millisecond or 10 millisecond timeout, then you just move on to a new host. And so this is actually part of our open function. So we use, to talk from PHP to Java, we use thrift. And so we actually this is a bit of custom thrift transport code that does this. And so to the rest of the system, it just looks like you're opening a socket connection. And if this succeeds, then you've connected. And if not, you just move on, given the number of connections you're willing to do. So this works really well. You know that when and we can show you the Java side, which is really just, and this is all we care about having the JVM execute is you're going to process, you're going to write these 4 bytes, you're going to flush them to the socket, and then you're going to go about how you normally would. And this is sort of the Java side of that thrift connection. But we've ensured that the JVM is at that moment running, and because garbage collections are either these, for the most part, either these tiny little millisecond events or these big old generation collections that take multiple seconds. We now have a way to very quickly suss out which of them is in the middle of those long collections and just move on very quickly within 1 to 10 milliseconds to another host. So it puts a certain constant time cost on every request, but for the most part, sending this banner, if the JVM is not garbage collecting, happens in less than a millisecond. But it doesn't solve all problems. What if that node is up and in the middle of your request? What if you have a 4-second request and 3.9 seconds into it, it goes into a massive garbage collection spiral, but you're still not going to get a request? Or even worse, what if you're 1 millisecond into it and then goes into a big spiral? You're still gonna pause. You're still gonna wait a long time. And so what we worked on is something called backup requests, which we shamelessly cribbed from Google's Jeff Dean. And I encourage you to read this paper and his more recent Tail at Scale, which is also very, very good. So backup requests are that you do a request, you wait a certain amount of time, say 50 milliseconds, and if you haven't gotten a response yet, you send it to another server, and whoever sends you a response back first is the one you take. So in that case, you're working around the fact that that first server might garbage collect somewhere in the middle. You've got a backup. And so this worked well for smoothing out things at the tail as well. And actually it's a little bit different because the servers that Google is talking about are all C++ servers, but it works well for us once you know that at that moment they're not garbage collecting. The backup requests work nicely. So sharding, so if you have a sharded service, that actually brings up interesting problems in that let's say you're sending it to a server and that server is doing a fan out to lots of different servers, and one of them happens to be paused or garbage collecting or unavailable at that moment. You're going to be bounded by the slowest one of those services you're fanned out to, which is another place you're going to want to have backup requests. So that's another useful place for that. And actually, on our search stack, there's something we're working on trying to integrate into Solr for sharded Solr. So the philosophy being that you want to make a reliable whole out of unreliable parts. So instead of trying to stamp out every bit of latency you can, every bit of unreliability, acknowledge that you're going to have a certain amount of unreliability and try to make a reliable whole out of the unreliable parts. Any questions? No? Okay. So let's talk very briefly about memory leaks. So as Mike mentioned, we had previously had very big garbage collection pauses. The biggest contributor to those ended up being memory leaks. So it's hard enough work to collect the heap when it's collectible, but when you have leaks and you can't actually collect every object, it becomes even harder. And so we had some leaks, and the way we found them, so this is in our Solr stack, but I think it's a sort of a generalizable technique, is that we have things that are sort of age-based. These in the Solr world, they call this the searcher, and every time your index gets updated, a new one of these objects is created. It initializes some caches, does certain things, and so each little generation of your search index does a new one of these things. And so I suspected we had a leak of this type of object. And I suspected this type of object was then holding on to lots of other objects, and that's why we were seeing these pauses. And so YourKit that I mentioned previously has some nice tools, and this probably exists in other profiling frameworks as well. But what you could do is you could do things inside of the code it has that instruments classes. You can actually put little hooks in there and do certain things. So in this case, every time one of these things got created, we advanced the generation of every object that was created. And so you could look, an hour after one of these objects that should last for, say, 5 minutes was created. If you're on generation 15 and generation 15 is the live generation, and you take a snapshot of your heap and you still have things from generation 2, that's a pretty good sign that you've got a memory leak. So this is a really useful technique, because I generally find that age-based objects are a big source of leaks. If you have things that get cycled in and cycled out, that's a big source. So this has been a very useful technique for us, and has been responsible for finding most of our big leaks. All right. So there's no questions. I'm going to go to some miscellaneous topics.
Do you guys use profilers as well to try to find some of those leaks?
So YourKit itself is sort of a profiler. So in addition to this stuff, on some of these other tabs, you can see it does CPU profiling, memory profiling, GC profiling. The CPU profiling is great because you can do both sampling and tracing, so it can just grab certain instructions and has a reasonably low enough overhead that you could run it with a real application load. And then if you want to count basically how many times every method gets invoked, you can do tracing. One thing I would say to not do is, even though it's the lowest overhead JVM profiler that I know, don't leave it running in production accidentally, because we've done that and it doesn't go well. So we actually saw weird spiky garbage collection behavior for a month, and it was my fault. I just left the profiler running, and so it's make sure you turn it off when you're done. But it works really well. It's very low overhead, but it's not zero.
So with the panel protocol, do you get any numbers as to how many times the request had to be made to another server?
Yep.
It had to actually travel to the server.
We do, and I removed a lot of the logging, but in the actual code, like between every one of these logs, we use statsd, another piece of Etsy infrastructure to log which server, which request, how many times, and when we've had.
That's on the client side too, right? The client connecting to the server saying I didn't make a connection.
Yep.
Okay.
Yeah, the client will say, I tried to connect to Search 50, Search 50 wasn't up. The Search 50 gave me a straight up TCP connection failure. Search 50 gave me a banner timeout, or I waited for those 4 bytes, I never got them. Or it'll get I actually got bad data, or it got I waited 10 milliseconds, it didn't happen. Other things we've experimented with in this variations of this is exponential backoff. So let's say you have sort of general network. So for the most part, within a quarter of a millisecond, you'll get that banner back inside of a data center. But sometimes there might be sort of general network congestion, and nothing's going to come back in a quarter of a millisecond or a millisecond. Everything might come back in 7 milliseconds. And so if you can have some intelligent back off, you'll be able to get successful requests in there, but you'll still optimize. So we've experimented with that as well.
Do you know like any percentage of requests that actually had to do a secondary query to understand? I mean, it's just all.
When we've had really, really bad systemic GC, when we've had memory leaks, it would be like 50% of the pool at certain points would be busy doing full garbage collection. So it's gotten as high as 50%. I mean, I'd say in a normal day, it's going to be something like 1 to 3%, basically aligning with the percentage of time that the VM is garbage collecting. But yeah, but it's been really nice to have a situation where you can tolerate that sort of unreliability, where you could have a memory leak. Especially you're writing applications very quickly. Sometimes you're gonna break things. I'd say if there's any lesson that has been the most important during my time at Etsy, it's that when you build distributed systems, the least reliable component in the entire system is the people that build them. So forget about network failures and hard drive failures. The people involved fail 100 times more. I am far more unreliable than any solid state drive. I'm going to break things every day. So if you can design systems to be resilient to the people that are going to work on them, then you've really got something. So if you can acknowledge your own weakness, you'll build better systems. Let's see. How are we on time?
How much do you need? I think we're all right.
Okay.
Probably like 10 minutes.
Okay. So question about system GC comes up sometimes. Should you manually invoke the garbage collector in any system, or is it better left to the VM? In general, the rule in the JVM is you always want to let the JVM decide. It knows best when to invoke garbage collection. You don't want to be, after every request, having to manually invoke system GC. It's probably indicative of larger problems. But the one time that we do it is when a server boots up, does a lot of sort of initialization. It does caches get warmed, things get cycled through. Right before we flip the socket on to listen for requests, we'll system GC. That's sort of like the only place that's the only place we feel like we actually know better than the JVM whether we should be manually garbage collecting.
Right, but even then it's just a suggestion, right?
That's true. It doesn't have to do it. It could deny our request. We can't force it if it doesn't want to. Compressed oops. This is whether you should use compressed ordinary object pointers in the JVM. And if you have a heap that's less than 32 gigs, which is why we have that magic 31 gig heap, you can use compressed ordinary object pointers, which instead of having 64-bit pointers, you can have 32-bit pointers, so it saves you some space. So be careful as you're growing your heap. If you cross the magic 32 gig threshold, you can no longer use compressed pointers. NUMA, so these days not all memory is equally accessible. So not all memory is equally close to every CPU. So one thing we've played around with a little bit is non-uniform memory access and allowing the JVM to take advantage of non-uniform memory access. So if you think of the traversing of the heap, if every time you're traversing, you're moving around from one bank of memory to another bank of memory, and that's super expensive. That's going to be even more expensive, but if you can the VM can take advantage of memory being close to the CPU. The closer it is to the CPU that's doing the work, the cheaper that's going to be. So this is something to keep in mind. And actually, one of the reasons we want to have smaller heaps than our 31 gig heap is to be able to have the heaps be small enough that we can keep all of the memory that a single CPU might need local. So it might be anywhere between 50% faster to access a local bank of memory than one that's sort of across the board. Paging is a big issue. So you don't want your heaps memory pages to get paged out to disk. This is death to garbage collection. We thought this was actually what was happening to us. It wasn't, but we were concerned about it enough that we did some monitoring. And so if you're having bad garbage collection problems, definitely take a look at are there things on the box that are taking up so much memory? Maybe you have a batch application, maybe you just haven't given enough RAM to your process. Something spins up and uses enough memory that you get paged out to disk. That's going to be really slow. But it's very simple to measure this. This is a little script we have to measure it, where you can look at minor and major page faults. And major page faults is going to be your VM's pages getting moved to disk. And then we just spit this to graphite, and then you can graph. So if you look at our JVM GC graphs, they also track VM pages getting paged out to memory, because we know that would be death for garbage collection speed. And it's very easy to monitor. You can do it per process. So let's say you are having paging problems. How do you solve them? One is just buy more RAM, because ideally you have enough RAM to keep your JVM in memory. And whatever data you need to access frequently, you want to keep that in the operating system's file buffers, and have enough memory that whatever else happens on the box, you don't get paged out. But let's say, and then another thing you can do to try to tell the VM that you don't want to be swapped out is to turn off swappiness. So that's a little trick to get Linux to be less swappy with memory. There's fascinating threads on some of the Linux boards about the swappiness parameter and how it works. I won't try to replicate. But let's say you really, really, really don't want your pages swapped out. You can use a system call called mlock or mlock all, where you mlock every page. So you're basically telling the operating system, no matter what, don't page my memory out. And if you look in the main method of a lot of JVM-based servers, Cassandra, Elasticsearch, they'll have an mlock all call, and they'll lock all the JVM's pages in memory. And so actually the last time I gave a talk about mlock, one of the guys from LucidWorks went and wrote a little Java agent that you could actually start any Java process up and not even put it in your Java code, and basically it will you could use some parameters in the agent just in the command line to basically tell your JVM to never to mlock every single one of your memory pages. So it's a pretty neat little thing. If you're having paging problems, I would give that a try. And then finally, if things get really bad, you don't want Linux to kill your process because it's out of memory. You could basically ask for mercy from Linux's out-of-memory killer and give it this magic -17 to procpid umadjust, and that will basically tell it to leave me alone, find someone else to kill. So that's kind of neat. And then finally, there's huge pages. So in newer kernels, you can have larger memory pages. So I think by default they're 4K. No, the default page size is 4K, and huge pages are about 2 megabytes. So it can actually make a lot of things a lot faster if you have fewer memory pages to manage. In 4K, if you've got, let's say, 96 gigs of RAM on a machine, that's a lot of memory pages for the OS to manage. If you give it 2 meg pages, it's many fewer. Another thing you could try is always pre-touch. So to have the JVM pre-touch all the different memory pages. It'll add some time to start up, but every memory page you use is going to be initialized. So finally, a couple of quick things about future directions. As I mentioned, so our current heap for our main process is this 31 gig heap. And we've been through a lot of pain with garbage collection. So one of the things we're working on is splitting it up and sharding it into lots and lots of little JVMs. So there's other advantages to this. There are certain optimizations that the VM can do when you have below 4 gigs even, and below 32 gigs, you can use the smaller ordinary object pointers. But basically, the less memory there is, the less work the JVM is going to have to do. And so for our search applications, it's a natural fit. We can shard them. They parallelize reasonably well. And as much as you get parallelism at the garbage collection level, if you do, let's say, an old generation collection, and you use the throughput collector and you tell it to do work in parallel, it will parallelize, but it's not embarrassingly parallel. If you have a 32-core machine, as we do, we'll get about 10x parallelization. But we won't get 32x, which means you're leaving some CPU on the table. So one thing you could do is if you took that 31 gig heap and you had 32 1 gig heaps, each of them pinned to a particular CPU, then you could get all 32 CPUs being used. Another option which we've considered here and there is using off-heap memory. The JVM, Sun JVM at least lets you use the unsafe operations and go off-heap and reference things off-heap. That comes with its own set of complications, but that memory is not managed by the garbage collector. It doesn't need to get garbage collected, but you're responsible for then managing it. So there are certain use cases where we're looking at that. We're also going to look at the G1 collector again. We tried it a few years ago. It's probably the most promising looking of the JVM collectors, but when we played around with it last year and the year before, it was still very new. But I've heard a lot of great results from other JVM users recently. So especially in JDK7, that's something we'll look at. And we might play around with that commercial collector I mentioned from Azul. See what the budget is. Let's see, resources. If you're interested in garbage collection, and who's not, I recommend that you check out the garbage collection handbook. It's great. It's basically there's one book on garbage collection. This is it. A new edition came out last year. It's really comprehensive. If you want to understand how this stuff works, this is great. If you're working with the JVM, also check out Java Performance. It's a pretty recent book. I feel like it hasn't gotten a lot of attention, but it's very thorough. If you want an overview of the different collectors, another one of the Lucene guys has a good sort of boot camp where it'll teach you about all the different collectors and some of their settings, some of the pluses and minuses of each. And Gil Teen's talk on understanding garbage collection is terrific. He is the author of that very excellent commercial collector, so he knows his stuff. And this is a great paper from a guy at Intel, what every programmer should know about memory. This is really terrific. And a neat utility that I found, there's a lot of JVM options, and it's very difficult to find documentation for them, but there's this neat little GitHub project where it gives you like a little searchable reference to every single garbage collection, every single JVM instruction, at least on the Sun JVM, and it tells you what the default values are, what it takes. It's really useful. Then also, don't be afraid to read the JVM source. Like if you're not really sure what a particular option is doing, you can just act the source. It's actually reasonably approachable. And it's actually answered questions for me about stuff like how does system.identity hashcode work in the JVM? If you have a hash code where you're going to get the same hash code for an object throughout its life, and then you say, wait a minute, the JVM is moving memory around. How does that work? It wasn't clear to me until reading the JVM source. It's reasonably approachable. And stuff on Stack Overflow will be out of date, but the JVM source code won't. This is a really cool Google group if you like geeking out on this stuff. The Mechanical Sympathy blog, sort of the union of hardware and software. It's sort of a great computer architecture Google group. So if you're into the JVM especially, and high performance JVM stuff. So let's see. Thank you for coming. And let me know if you have any questions.
Can you just talk quickly about the whole backup request concept again? I think I kind of missed that.
Sure. So the idea is that, for us, even once we find a server that we know at that moment is not garbage collecting, we don't know that over the course of the time it serves that request, it might be a request that takes 2 seconds. At some point in there, it might go into a full garbage collection that takes 10 seconds. And so if we were to wait till the end, we might be waiting 12 seconds to get a response. And so sort of inspired by Google, we built something where we'll send a request to server A. Once we know that it's not garbage collecting at that second, and then a certain amount of time into the request, say 50 milliseconds, 500 milliseconds, maybe depending on what type of request and what the anticipated PERC 95 performance for that request is, then you send a backup to a separate server in parallel. And then whichever one comes back first, you take that response and then just discard the other one. Google does even cleverer things where it sends a request to server A, sends a request to server B, and then whichever one is done first, it will go to the other server and cancel it, just to reduce the overall system load. So that's pretty fancy. We don't have that, but we would love to. But so that's the basics. And that's really great for sort of smoothing out, let's say PERC 99 performance or PERC 98 performance. Really trying to get the stragglers down. But you have to balance that with overall an increase in system load. I mean, you're going to sometimes you're going to do 2 requests for every where you would normally do 1. So it's an increase in overall system load. So you've got to balance that with the benefits at the tail of requests. And I think that's where knowing how long to wait, given a certain request, comes in.
This backup request, is it only for the get request or the post request also? Because in post, you might end up creating 2 entries in the backend.
Totally. This is all for read-only requests. I've been working on search for so long, I can't even give you a good answer on what we would do with a write request. I'm not sure. I'm not totally sure what you would do with a write request. But for read requests, it works reasonably nicely.
In application code, have you tried anything or used anything with, like say, weak or soft references as caches or different tricks like that?
Yeah, we've actually had some difficulties with weak references. We've had problems with weak references, specifically with their interaction with the CMS collector. There's been some bugs in that that actually recently bit us in Hadoop even. We had a bug with weak references. I'm kind of down on weak references as a way of managing memory, just because it's a little too non-deterministic. So I'd rather see those things explicitly freed when they're not used. So we've had some places where we use them, and Solar uses them here and there. But yeah, our preference is generally to programmatically free stuff up rather than add that to the reference processing list. It's very easier to reason about. Yeah.
Could you say more about memory leaks? How they interact? You said something about age-based.
Yeah. So the memory leaks that really got us were really leaving around straggling references to objects that should have been cleaned up. As things aged out. We update our index every 10 minutes or so, and so we had these caches and sets of objects that every 10 minutes in Solar, there's sort of the new thing comes and it gets warmed up, and the old thing, and once it's done, the other one should go away. But we had sort of dangling references and something in a static, and there are actually other tools out there that I've not played around with. One called Plumber, Plumbr, that promises to sort of deterministically find every memory leak in your application using certain heuristics. I don't know how that's possible, but maybe they do a good enough job that they find some for you. But yeah, I mean, if you find like your old generation just never getting any smaller, that's a good sign that you've got a memory leak. If you've got a big old generation collection, and you should have a pretty decent idea of what your resident sort of old generation data set size is. What are the sizes of the caches that you expect to be there for the lifetime of the application? About how big are they? And it's a bad sign if those just grow and grow and grow.
Would you mind talking a little bit about the web container used at Etsy? Like any tricks or anything that came up there?
The web container?
Yeah.
So the web. Let's see. Well, on the Java side, we use Jetty is the container, but to deploy web applications. But in our case, the only web application we have some custom monitoring and metric stuff. But for the most part, it's just Solar is the only Java web application we have. Jetty works really well. I'm excited about Jetty 9. It's actually interesting stuff in that mechanical sympathy group about Jetty 9 and memory alignment, which is something that doesn't come up very often. If you have memory being accessed to taking advantage of those sort of L1 and L2 optimizations. So if you can find that post about Jetty, it's really interesting. On the web side, it's Apache and PHP, which actually is new for me at Etsy and presented challenges to me because I'm used to JVM talking to JVM and long-running processes with connection pools talking to other long-running processes. So it's been interesting to think about these sort of short-lived PHP processes that are always opening up a fresh connection on every request. But it's nice in a certain way that it contrasts to the JVM and that you don't have to worry about long-lived objects and connection leaks and old generation collections.
How many services do you consume on each request, and how do you tune that parameter?
How many services do we tune on each?
From like the PHP side, how many connections are you opening to JVMs to consume either search or user alt or anything like that?
Yep. So search is one of the few services. So for the most part, at Etsy, everything is PHP. There's very few services. I mean, Memcache, payments, MySQL, if you consider that a service, and then search. But we don't have sort of a separate user service, a separate favorite service. At least at this time, and things are all within the single PHP process, which Mike can give a better talk on than I can. But so yeah, so actually in some ways it's been we've sort of had to figure these things out on our own in terms of search because we don't have a ton of other service infrastructure, and so some of these things we sort of felt around in the dark and found ourselves. But it is as you have more services to talk to and you have more points of failure, or if you have web requests that really want to hit a lot of different things in parallel, that it brings up a lot of those questions, which we're sort of starting to address.
Have you also worked with PermGen memory?
With
PermGen?
PermGen? No, we have not had problems with PermGen. I think probably the reason we haven't had it is so PermGen being the part of the JVM that the class data is in. So if you've had the JVM out of memory on you due to a PermGen error, it's probably because you're deploying to Tomcat and you're doing your 10th deploy of your war, and Tomcat is not properly cleaning up the older versions of the classes that you were deploying, and you blow out the PermGen. Interestingly, in Java 8, they're getting rid of the separate PermGen area. I'm not exactly sure how it's going to work, but PermGen itself is actually part of the collection cycle and interacts with the rest of this. And you want to give it a certain maximum size, but you don't want to give it too much. I think the PermGen gets you a little bit when you want to do microsharding. If you want to have very, very small, let's say 256 meg heaps and have 100 of them on a machine, you can't forget you have this constant cost for all of those classes you're going to load. You're going to load all of the classes in every single shard. So that's going to cost you somewhere between 30 and 100 megs per instance. It's not like a shared pool. So that's one thing where you got to keep in mind when you say XMX 4 gigs. It's not just the JVM's not going to use just 4 gigs. You got to add the PermGen as well for the class data.
You consider or are you using any APM tools like Dynatrace or Dynamics?
We have, so for the most part, we write a lot of that stuff ourselves. We've played around with New Relic a little bit. We're friends with Otis over at Semitext, who has this nice SPM solar performance metric. So if you're using Solar and Lucene, it's really quite nice. But for the most part, yeah, we write a lot of this stuff by hand. We'll pull things out of JMX and spit them into Gangly and Graphite, and then our performance monitoring tools are really just sort of hand built on a lot of the stuff that Mike has written, Logster and dashboarding, and we just send it data. And
you should really try it because it supports PHP and Java too.
Yeah, Dynamics.
App Dynamics and
Dynamics.
And Dynatrace.
Dynatrace, I think I've played around with.
Maps out the whole infrastructure and everything. Like it maps out from the very entrance call to call in the database, so you can see you can call all the calls.
We have sort of a very lightweight version of that because we've used New Relic for that similar sort of end-to-end monitoring of a request comes into PHP, it spends this time in the controller, then it goes to MySQL, then it goes to Memcache, and you can sort of drill down and slice and dice that stuff. We have a sort of very lightweight version of that called IO Profiler. Where you can you go to any Etsy page and just append a URL parameter, and it'll sort of spit it out in an HTML table at the bottom. All of those details. So you can sort of the most lightweight thing we have. It'll show the call to Solar, the Memcache call. You can sort of drill down into it. And then we also use Splunk to connect a lot of that stuff. You take the UUID of a particular request and you can trace it through. Cool.
All right. So,
thank you very much.
Thanks again to Gregg Donovan. I also want to mention, actually, I'm going to put you on the spot. You have a bunch of references, books, blog posts, source code, and things like that.
Yes.
So we're going to get the slides online so we can all see them later.
Of course.
Awesome.
Of course.
We'll post those to the meetup. I want to thank Jolly, actually, for showing up and recording. Anybody who's watching in the future, welcome from the past. And again, thanks to 10Gen for hosting. Thank you very, very much. Have a good night.